Problems in air conditioning generally fall into two categories: refrigeration equipment problems and control system problems. This video will help you determine if the problem is in the contactor, and if so, how to repair or replace it. To prevent unprofitable service calls, question homeowners when they phone. Ask if they've checked the setting of the thermostat. Is it calling for cooling? Have they checked fuses and circuit breakers? Is the system running but not cooling? Or is it not running at all? If the compressor and fan are running but are not cooling properly, it's probably not a control problem. You'll probably want to start with the refrigeration system. If the system doesn't start at all, or starts and runs without stopping, the problem could be in the contactor. In a system that doesn't even start, set the thermostat for cooling. Observe the contactor to see whether the contacts close. If contacts do not close, check the voltage at the coil terminals. If the voltage is normal and the contacts are open, you've probably got a burned out coil. If the contactor does pull in, your next step is to see if you're getting voltage through the contacts. Arcing burns away the contact surfaces and prevents conduction of current through the contacts. Now, back to the coil voltage check. 0 volts on the coil indicate a power supply or control circuit problem. A contactor that buzzes but does not pull in probably indicates low control circuit voltage. Check the voltage at the coil terminals. The voltage on the contactor must be within 10% of its rating. A mechanical problem with the contactor armature can also keep it from pulling in. If that's what you find, you'll have to replace the contactor. If voltage is not within 10%, some possible causes unrelated to the contactor are an undersized transformer, insufficient input voltage to the transformer, or thermostat wires that are too long. These conditions reduce voltage below a coil's operating voltage. To illustrate the effect of improper voltage, we connected a variable voltage source to a contactor. As the voltage increases, it becomes noisy, but the contacts don't close. Increasing the voltage to normal causes the armature to pull in and the contacts to close. If the contacts close and the system does not start, listen to the compressor motor. If it hums but doesn't run, most likely the problem is in the equipment, not the contactor. Normal contacts are either clean or black. You should see a uniform wear pattern. A speckled appearance is normal. Contacts are bad if excessive material is burned off. They show a pattern of uneven wear, or they are delaminated or peeled. It is also possible for the contacts to weld together as a result of excessive current draw. Although you must replace the contacts, also check the equipment on the line to determine the causes of the excessive current draw. If the contactor is too small to handle the load, the result is the same. If the system starts but rapidly cycles or locks out, check to see whether the compressor is cycling on overload, high pressure, or low pressure. When replacing a contactor, compare its contact rating with that of the replacement. The new contactor ratings must at least equal the old contactor. And by using a replacement with a somewhat higher contact rating, you buy extra reliability and service life. And of course, you need to compare the physical size of the old and replacement contactors to ensure that the replacement contactor fits. If you determine that the contacts are bad, remember that you have the option of replacing just the contact. After disconnecting the wiring and opening the top of the contactor, you are ready to take out the contacts. The terminal ends of the contact screw to the contactor frame. Springs hold the shorting bars in place. Complete the repair by thoroughly checking out the contactor. Whether you decide to replace or repair depends upon a number of factors: total cost to the user, type of service, and availability of replacements. You can also replace burned-out coils. Disconnect the power and remove and label all the wiring connections. Remove the screws from the mounting plate. Carefully take it apart. Note the position of the coil terminals. Carefully insert the replacement coil. With the magnet lamination nested in the base, replace the base on the arc box and firmly fasten the screws. Restore power and check contactor operation. Sometimes the location of the contactor may cause operating problems. If the coil voltage is low, check to see if the thermostat leads are too long. If line loss becomes excessive, it results in low voltage at the contactor coil. You may need to install heavier wire. High temperatures can also be a factor. For example, an area that exceeds 150 degrees Fahrenheit causes the coil to lose its efficiency and operate incorrectly. If the contactor is located on the roof or another outside location, inspect the contactor to ensure that rusted and corroded terminals are not causing problems. If the contactor has an auxiliary switch, inspect it to ensure proper operation. The principles involved in air conditioning control are quite simple, and if you have a good understanding of these principles, you're well on your way to being able to handle any troubleshooting jobs that you encounter. When confronted with the word transformer, the average person today probably thinks of the child's toy that can take on a variety of futuristic forms. Most technicians would say that a transformer is a power source in electrical circuits. But beyond that, they probably don't spend a whole lot of time thinking about transformers. After all, transformers last for years. If one burns out, you put in a new one. The brand isn't important because they're all the same. Or are they? That's one of the important questions that will be answered in this program on transformers for low-voltage control circuits. Every air conditioning system has two basic elements: the refrigeration equipment itself and the low-voltage circuit which controls that equipment. A transformer serves as the power supply for the control circuit by stepping down the line voltage. Even in simple cooling systems, control circuits pull a heavy load. At minimum, the transformer has to power a contactor and a fan relay. The contactor takes the most power. It's a heavy-duty switch that turns on the compressor motor and often the condenser fan too. All transformers, regardless of size or application, are built on the same principle. Two coils of wire, called primary and secondary coils, are combined with an iron frame. When voltage is applied to the primary coil, current is induced in the secondary coil. The secondary's output voltage is determined by the relative number of turns in the two windings. In a step-down transformer, the secondary has fewer turns than the primary, so voltage is lower in the secondary. The opposite is true in a step-up transformer. In either case, energy transfer between the two coils is never 100% efficient because resistance and other factors cause heat buildup. Heat, of course, is the enemy of electrical equipment, and one important measure of a component's quality is how well it controls heat buildup. A transformer's capabilities are indicated by its electrical ratings. These include the voltage and frequency of the primary and the voltage and load rating of the secondary. The load rating is expressed in VA, which is volts multiplied by amperes. Class II circuits, as defined by the National Electrical Code, are energy-limiting circuits. The maximum secondary current load is 3.2 amps at 30 volts, and the maximum load rating is 100 VA. If the circuit draws more than 3.2 amps, a fuse must burn out or some other type of overload protection must stop the flow of current. The major advantage of a Class II circuit is that it can be safely wired at very low cost. Thermostat-type wire can be used, which is considerably easier and less expensive than running conduit. In addition to meeting the NEC code, Class 2 transformers must pass a burnout test to meet UL safety standards. There are two categories of transformers. General listed transformers are suitable for field installation. Component recognized transformers are designed primarily for use by equipment manufacturers. NEC classifies transformers for Class 2 circuits as Class 2 not wet and Class 3 wet. Essentially, these classifications define where a transformer may be safely located in terms of its exposure to moisture. Different types of overload protection may be used in Class 2 transformers to meet UL safety standards and the NEC code. One type uses a non-replaceable fuse that opens to prevent excess current flow. The fuse may be activated by either heat or current and may be located in either the primary or secondary winding. Other transformers are designed with enough impedance to prevent overheating, so they don't need fuses. In such transformers, voltage drops off very rapidly when there's an overload. Now that you have a better understanding of Class 2 control circuits and the various transformers that can be used in them, let's look at how to troubleshoot possible transformer problems in an air conditioning control system. In our first example, we'll assume that the system has failed to start. Check to see if the contactor has pulled in. If the contactor is open, check the voltage at the coil. If it won't pull in with the proper voltage in the coil, the contactor is bad and must be replaced. Zero voltage means the problem could be in the transformer or somewhere else in the circuit. So check the voltage at the transformer secondary. If it's normal, within 10% of rated voltage, the transformer is okay. If voltage at the secondary is zero, check the line side of the transformer next. Normal voltage going in, but none coming out, means the unit has faulty wiring or is burned out and must be replaced. Now let's go back to the contactor again. If the contactor groans or hums but won't pull in, low voltage may be the problem. Check for an undersized transformer and or low voltage at the primary side of the transformer. Supplying abnormally low voltage to the control circuit can cause chattering or sticking contacts, burned out coils, or improperly closed contacts. They in turn can cause faulty operation of the compressor motor. So selecting transformers of adequate size is very important to the performance and lifespan of electrical components in air conditioning systems. For service work, there are two useful rules of thumb which will help you choose the right size transformer. It's usually a good idea to replace a burned out transformer with a bigger one. The cost difference is negligible, and the larger size gives you an extra margin of safety. When adding a component, such as a humidifier, check the manufacturer's recommendations. Generally, you want a transformer with a VA rating about 20% higher than the combined operating VA of all the components being controlled. Size, however, isn't the only consideration. Quality and performance are also important. Remember, not only must a transformer be able to carry the continuous current of a circuit's components without overheating, it must also be able to handle inrush or startup loads. It takes more current, for example, to pull in a contactor than it takes to hold it in. Some transformers, however, fail to deliver adequate voltage under heavy loads, and size isn't always the problem. If a transformer's voltage drops off too much under inrush conditions, it may not be able to pull in all the necessary loads simultaneously. Some control systems are very sensitive to input voltage and simply won't operate if it drops too low, say below 20 volts on a 24-volt system. On the other hand, voltage that is too high can also cause problems. This is important to remember because lower quality transformers often compensate for poor voltage regulation by using a higher secondary voltage. Under light load conditions, high voltage can damage coils and other control circuit components. Department tests show that high open circuit output voltage can also cause the thermostat to cycle the system too rapidly on cooling loads, because of increased cooling anticipator heat output. The result can be overcooling and increased cooling cost. Some systems require a 26-volt open circuit, and if you hit them with 29 or 30 volts, the system's logic may lock up intermittently. If you run into a situation where open circuit voltage is up near 30 volts, you may also find that its voltage falls off very rapidly as you load it down. The key point here is that different transformers with the same VA rating can indeed have quite different capabilities. The simplest way to avoid problems with voltage regulation is to select transformers that meet the NEMA standard for Class II transformers. The key requirement of the NEMA standard limits the amount of output voltage drop-off allowed as the load on a transformer increases. At 100% of rated load, a transformer must hold its voltage within 1 volt of its 24-volt rating. Open circuit voltage must be within a half volt of its 26.5 rating. At 200%, it must be within 1.5 volts of its 21.5 volt rating. The dictionary says, a relay is an electromagnetic device activated by a variation in conditions in one electric circuit and controlling a larger current or actuating other devices in the same or another circuit. Such definitions tend to cause eyes to glaze and brains to short circuit. A simpler way to put it is that a relay is an electrically operated switch. Relays come in a mind-boggling array of sizes and shapes because they have an enormous variety of applications. Almost anything that has an electrical or electronic control system uses relays. In heating and air conditioning systems, very tiny relays are used in thermostats, and larger ones have a variety of other applications. Relays control fan switching in air conditioning systems and switching for burners, central circulators, zone circulators, and heat elements in heating systems. Relays are the mediators of electronic systems. They make it possible for different circuits with different voltage and load requirements to work together for effective control. While there are many types of relays, they're all built on the same principle. A coil is wrapped around a magnetic core. When current flows in the core becomes magnetized and attracts an armature, closing the relay's contacts and turning on the power in one or more circuits. When current to the coil is shut off, springs return the armature and contacts to their original positions, turning off the power in other circuits. One key feature of a relay is that very little current is needed to energize the coil and switch the contacts. As a result, a small switch, like a low-voltage thermostat, can be used to switch line voltage circuits and control fans, compressors, and other equipment. A relay with properly rated contacts can also switch circuits with lower voltages than the control circuit. For example, a 24-volt thermostat circuit controlling a millivoltage gas valve. Relays have two other very important characteristics. First, they provide electrical isolation between the control circuit, the coil side, and the circuit being controlled, the contact side. Second, a relay can control a number of outputs from a single input, and these outputs can be isolated from each other electrically. We'll be going into a lot more detail on specific applications for relays shortly, but first, let's review some relay ratings. As a rule, when selecting a replacement relay, the only things you have to know are coil voltage, contact current ratings, and the switching configuration. But there are a few other ratings you should be familiar with. Coil ratings describe a coil's characteristics as a user of electricity, because a coil is an electrical load in the control circuit. Nominal, or rated voltage, is the rated voltage of the coil. And in 95% of all applications, that's the only coil rating you have to know. Pickup voltage is the lowest average voltage needed to pull in a relay. Dropout voltage is the minimum needed to keep the contacts closed once a relay pulls in. The terms inrush and sealed relate to how much power and/or current is used to pull in a relay versus how much is used on a continuing basis after it has pulled in. Coil ratings which use these terms include nominal and maximum sealed VA, nominal and maximum inrush VA, sealed and inrush amperes, and sealed wattage. The term VA stands for volts multiplied by amperes. When it comes to contact ratings, the most important things to know are how much current the contacts can handle and the type of load the rating applies to. Many relays are rated for several different voltages, and normally load ratings apply to each pole. Inductive full load, or sometimes amperage full load, is the number of amps a contact can handle on a continuing basis, such as a running motor. Inductive locked rotor, or amps locked rotor, relates to the instantaneous current flow a set of contacts sees when starting an inductive load such as a motor. The resistive rating tells how many amps a contact can switch when controlling a resistive load, such as an electric heater. The resistive rating is normally higher than the inductive because resistive loads cause less arcing. Horsepower is the approximate size of the biggest motor a relay can switch. It's important to remember, however, that different motors with the same horsepower rating can have very different current ratings. So be sure the full load and locked rotor ratings of the motor and contacts are compatible because they're more accurate than horsepower. Pilot duty is a rating applied to very small inductive loads, usually solenoid or coil, with a top power factor of 40%. Some Honeywell relays have both power poles and pilot duty poles. Power poles are rated in full load and locked rotor, and pilot duty poles are usually rated in maximum and minimum VA. Maximum VA is the most the contacts can handle without burning out prematurely. Minimum VA is the lowest power that can be reliably switched. Minimum on pilot duty contacts is usually about 3 VA. Contact resistance is important when switching very low currents, such as in millivoltage circuits. Load-rated contacts have flat surfaces that can collect dust or silver oxides. Heavy loads, or line voltages, can blast through this, but light loads sometimes can't. So it's important to remember that relays used in millivoltage circuits should be rated for that service. Some Honeywell relays use gold flashed contacts for reliable millivoltage switching. A thin layer of gold on these contacts produces very low resistance and also guards against corrosion. Okay, now that you're familiar with the rating system, let's take a look at the switching requirements for air conditioners and the relays they use. Residential systems require compressor switching and fan switching. The compressor, of course, pulls the biggest load. In systems with air-cooled condensers, the condenser fan is wired in parallel with the compressor, and that adds to the load. Contactors, which are basically big relays, are normally used for compressor switching in larger systems. Fan relays make it possible to control fan operation with a thermostat that is not rated for direct switching of the load. In a typical system, a call for cooling from a 24-volt thermostat energizes the fan relay coil. Then the contacts pull in and activate the 120 or 240-volt circuit for the indoor fan, turning the fan on or switching it to a higher speed. Honeywell's R8225 is a fan relay designed to provide low-voltage control of line-voltage fan motors and auxiliary circuits in cooling, heating, and commercial refrigeration systems. The R8239 fan center performs the same switching functions as a fan relay, but in addition, it has a transformer and a terminal board for convenient wiring of the low-voltage system. The transformer meets the NEMA standard for Class II transformers and is big enough to power the fan relay, the compressor contactor, and the controls for auxiliary equipment in most systems. The R8325 control center is basically the same as the 8239, but with a higher rated transformer and a lower current relay, it has more usable VA. When selecting a replacement relay for controlling a motor, the contact rating, amperage full load, must equal or exceed the motor's rating. Otherwise, the contacts will burn out very quickly and possibly cause serious damage to the motor. When matching a fan relay or center to a fan system, you should know the rated voltage, the current or horsepower rating of the contacts, and the switching configuration. Basic configurations include single-pole single-throw with normally open contacts, single-pole double-throw with one set of contacts normally open and the other normally closed, double-pole single-throw, and double-pole double-throw. In combination heating and cooling systems, single-pole single-throw switching is used when a relay's only job is to turn the fan on and off. When the thermostat calls for cooling, the relay pulls in to start the system fan. The switch that controls the fan in the heating mode is wired in parallel with the normally open relay contacts. Many combination systems have two-speed fans, low speed for heating, high speed for cooling. This requires a single-pole double-throw relay, as shown in this fan center hookup. The low speed for heating operates through normally closed contacts in the relay. On a call for cooling, the normally closed contacts open, cutting off power to the low-speed fan. The normally open contacts then close to energize the high-speed windings of the fan motor. Adding air conditioning to a power pile self-powered gas heating system is a common service job. To do that, a low-voltage thermostat and a transformer must be used to control the cooling system. Then, a relay with millivoltage-rated contacts, such as the R8222, must be added to permit the low-voltage thermostat to switch the power pile valve. While we've concentrated on air conditioning systems up to now, relays also play important roles in heating systems. Key functions include central circulator switching, burner switching, and zone circulator switching. Honeywell has 3 relays that can do a variety of jobs in heating systems. All have built-in transformers to provide low-voltage power for control circuits. The RA832 is used primarily for switching line voltage circulator pumps in gas-fired hydronic systems. It can also be used to switch millivoltage, 24-volt, or line voltage gas valves. The R845 is most often used to switch line voltage loads, such as zone circulator motors and line or low-voltage burners. It's especially useful for adding zones to existing hydronic systems. The RA89 is a heavier duty relay designed for loads up to 1/2 horsepower. Typical applications are switching fan and pump motors and small electric heaters. Honeywell has developed a special quiet operating relay, the R8229, for electric heating systems. The quiet secret is a nylon bumper that fits over the coil's magnetic core. The bumper cushions the blow of the armature when it pulls in, deadening the sound. For technical reasons, the coil of the 8229 is designed for direct instead of alternating current. A small diode rectifier on the side of the relay converts AC current to DC for the coil. The control requirements for electric heating are similar to those for air conditioning. Both require line voltage, heavy-duty load switching, and fan motor switching. In electric furnaces, heating elements account for the biggest load. One peculiarity of electric furnaces is that the fan must always come on at the same time as the heaters, because heat is produced almost instantaneously. 2 basic fan switching methods are used. In heat-only systems, the fan is usually switched by the same relay or contactor that controls the heat elements. In heat-cool systems, you might find a special thermostat that energizes the G, or fan terminal, with every call for heat. The Honeywell R8229 electric heat relay is rated to carry the combined load of the heat elements and the fan motor. This versatile relay can also switch auxiliary heaters and heat pumps. Honeywell's R8228 is a heavy-duty relay rated to switch loads up to 16 amps. It can be used to switch electric heat elements or large fan motors. Now let's review some general procedures for checking out and servicing relays. When a relay is not operating, the first thing to do is check the coil voltage to make sure it's within 10% of its rated voltage. If that's okay, check coil continuity by measuring the resistance of the coil. When a coil burns out, it usually becomes electrically open, so you'll get infinite resistance. Resistance of about 10 ohms means the coil is okay. You can also check the continuity of the contacts by disconnecting the relay from the circuit and measuring resistance across the contacts. You'll get zero resistance if they're closed, infinite resistance if they're open. On relays with exposed contacts, you should also check to see that the contacts are clean. You can also test the operation of a fan relay by applying power to the coil and listening for the click of the contacts. If the relay is okay, but the fan doesn't operate at high speed, you need to check the wiring and the motor itself. Troubleshooting relays is pretty simple, just a matter of comparing inputs and outputs. Once you've determined that you have the proper input voltage, it's easy to check for contact operation and to judge whether a relay is good or not. Honeywell's line of high-quality replacement relays includes models for specific applications and those that can be used by skilled technicians in a lot of different ways. Your understanding of how relays work, combined with your general knowledge of control circuits, are the keys to finding quick and accurate solutions to system problems.